I need to stop something at something. Sorry. Okay. Okay. So I think you can continue with this. I pull this out by the side. Okay. So we have something like this. Like this is BI star AI. Okay. So the left hand side. So these two things, are they the same? What do you think? So this
Only
and
one.
this, are they the same?
Only for real values.
Exactly. Only for real values. So if A, so they're same for any I, if and only if AI is the same thing as AI star, BI the same thing as BI star. Okay. So that means AI and BI are real. Okay. If they're complex, then this doesn't work. Okay. You can do a similar thing for this trace to show that whether it's a scalar product or not. Did anybody try this for the trace? Well, actually, before then, let's finish one thing. So you see that if instead, if we define AB, so this is a new definition. If you define this as sum over I, AI star, BI, okay, then you can see that if you do BA, it will be sum over I. What should I write first?
B star.
No, BI star. Okay. So I follow the same rule. Okay, and this is AI. So you see, if I now do a star of this one, that's complex conjugate of this one. I do this. I take the complex conjugate. Okay, if you take the complex conjugate of the complex conjugate, you get the same thing back, AI star. You see, this and this are the same. Okay. So in this case, AB is something as BA star. Okay. So that suggests that it could be a dot scalar product. Okay. So you need to do the other two tests to check whether it's a scalar product or not. Okay. Do you remember what the other two tests are? Or the other two definitions that have to be fulfilled by a scalar product? Do you remember what the other two are? Okay. Yeah, so you need to look it up. The other two, so the first one you checked. The other two is if I dot C with A, V plus BV, I should get A, that's the scalar product of C and V, plus B, then the scalar product of C and V. So you see A, I retain A here, so not A star. And I retain B here, not B star. And then the third thing is, actually two things. So UU must be greater than or equal to 0. And if it's 0, it means U is 0. Okay. Or else sometimes last time I wrote this as the null vector. Okay. So you need to check this to see that, okay, yeah. Vlad Mini, you are correct. Yeah. So you need to check this also for this one. Okay. Let's quickly check the one for trace. Trace of A. Okay. Transpose B. Um, how do you find the trace of the matrix M? So you just take the sum of the diagonal elements. Okay. So these are n by n matrix. So you just take the sum of the diagonal elements, and that gives you the trace. Is this clear? Okay. So for instance, if you have a matrix 3, 1, 0, minus 3, okay, you can easily find the trace. What's the trace of this matrix?
0.
Yeah. So you just add the diagonal elements together. 3 plus minus 3, okay, which is 0. So that's straightforward to do. Okay, Jean Bosco, you are correct also. Marcello must have told you this. If you multiply two matrices, let's multiply a matrix C and a matrix D. Okay. Let's think about if you multiply matrix C and matrix D, it will be something like this. They have to be compatible. Okay, so C and D. Okay. What you usually do is you multiply the row of one by the column of the other one, and that will give you the first element. And then you multiply the next row by the column of the other one, okay, and that will give you the next element. You can satisfy yourself that if you do CD, okay, and you take element ij of CD, it's the same thing as you have to sum C, I, K, D, Kj, and sum over K. So the elements of C, the row elements, for instance, sorry, this is too small. Okay. So the row elements are C11, C12, C13, and then the next row is C21, C22, C23. Okay. And then if you do the same thing for D, okay, and then it continues. For D, you have, let's call it D11, and then this will be D21, and this will be D31. Okay, and along is D12, D13, and this will be D22, this will be D32. Okay. So when you multiply them together to get the first element, you see, you multiply this one by this, okay, and then you multiply this one by this, and then you multiply this one by this. Okay. So in that case, you see, is to get the first D11 plus C12, D21 plus C13, D31. Okay. So you see, here you have index 2, index 2. Here you have index 3, index 3. Okay. So is 1, 1, 2, 2, 3, 3. So that's exactly what I've written here. Okay. This is, okay. And then this I and J lets you know that you are doing it for the new element I and J. Okay. So this is how you do the trace. Okay. Sorry, this is how you multiply matrices. Okay. So if I do this, okay, it's not the same thing. Okay. Because you see, this K and this K, uh, what before you can say that you're multiplying matrices, um, you need to have them in this position. Okay, so it's k here and k here, and then you know that you are summing over them. If you have them in this position, then you don't have what you are doing is not matrix multiplication. This is not matrix multiplication. The other thing is, of course, I can write. Okay, so this is fine. If someone gives you something like this, CKI, DKJ, okay, sum over K, can you write this in matrix form, like as matrix multiplication? If you wanted to do it as matrix multiplication, what can you do? So this one, I want to do it as matrix multiplication. What can I do? What do you think I can do? I need to do something so that this K, its position is here, and this I goes to this position is the other way. Okay. So a simple thing you can do is you can write, if you write it as DKJ, CKI, sum over K, this still does not help you. Okay, so I put this one first. It still does not help me because this inner outer index and this inner index are not the same. Okay, so you need the outer index and this inner index to be the same. In this case, they are still not the same. One simple thing you can do is I can flip this index Ki and write it as CIK. Okay, but this is not the same matrix. This is C transpose, and I write the IK element of C transpose. And then I have DKJ also, and I sum, I keep the sum. This new matrix, which I call C transpose, I'll tell you what it is just now. So this will give you C transpose D, element IJ of it. Okay. Oops, sorry. I think I'm switching too fast. Okay. So if I give you a matrix A, you can perform an operation which you call transposing. Okay. To get A transpose. Okay. The transpose of a matrix is just you make the rows into the columns. So that's it. So if I give you a matrix A, which is 4, 5, 6, 7, 8, 9, okay, you can trace the transpose of it. It doesn't have to be a square matrix. If I take the transpose the row and make it into a column, and yeah, so then 7, 8, 9. So this is the transpose. Okay. So if you take a matrix and you give me the ij element of the matrix, okay, then the transpose, the ij element of the transpose is the ji element of the other of the original one. You see, I transpose. So this one, for instance, you would have said this is A12. Okay. This is A12. Okay. Now in this, sorry, not A12. Not this one. Sorry, not this one. This one, A12. Well, A12. This one. Okay. So that 5 is now in this position. So you can see that this 5 now is A transpose, the element 2, 1 of A transpose. Okay. So you see that A transpose 2, 1 is the same thing as A12. Or in general, exactly what I've written here. That you see, when you make the row the column, you just transpose them, and this is what we have. So now let's look at what we had before. So we are supposed to find the trace of A transpose D. So I can write it as sum of A transpose D, the II element. Okay. So remember, the transpose is just you take the matrix, the II element of the matrix, and you sum. Okay. So what I've done now is the matrix now M is A transpose T. Okay. I take the II element. Okay. So now this one, what is this? This ATII. If you follow the rules I gave to you, it should be sum over J, A transpose, IJ, and then BJI. This I can write as sum over J, and I write this as AJI, BJI. And then this A transpose BII, I put it in, is sum over J, AJI, BJI. You can easily write this as sum over IJ, AJI, BJI. If you want to be clever, you can see that this is sum over lambda, A lambda, B lambda. Okay. Where in this case, lambda is the pair IJ. So you can see that this is just like a dot product for real numbers. Or dot or scalar product for real numbers. Okay. And in the first exercise, we already, this is a scalar product if the elements are real. Okay, so you can just use the proof of that to show that this trace is a dot product. Sorry. Then this trace is a dot product. Is a dot product for real elements. Okay. So the main thing is that I was able to show that it reduces to this, which is just like your vector A dot vector B. Okay, where the components of A are A1, are A lambda, A to represent this. Okay. So it just looks like that, and everything follows from there. Okay. So when you get back home or to your hostels, take a look at this again. Okay. What if A and B are not real numbers? Let's say they're complex numbers. What should we do? Okay. If they're complex numbers, we do the same thing that we suggested for the other case. Okay. So for instance, the vector AB, we suggest we suggested that we should write it as AI star BI. So in this case, also the dot product between matrix A and B, we should suggest also that it should be something like this: lambda, A lambda star, B lambda star. Okay. So if you put everything together back, you get A dagger and B. Okay. A dagger is not just the transpose. Okay. So A dagger IJ is not just the transpose. So you take the transpose of this, of A, and then you take the complex conjugate. Oops, sorry, made a mistake. So if you do this, then this is going to give you a dot product. Okay. Does anybody have a question? Okay. So we move on to the things we need to do for today. First, I need to check. If you have a question, let me know. So I'm going to show now the things we need to do today.
Hello.
You have a question I'm listening. Okay. So let me share again. Okay. So this is the stuff we need to do today. Because it's the last day of the week, so you will do a little revision. I already told you that you need to read to know what a group is. Okay. So I didn't teach you explicitly, but I sent you a link. You should read and learn what a group is. So if you do that, you should be able to answer the first question. Okay. So G is the set of all 2 by 2 matrices with complex elements, but having a determinant of +1. Does this form a group under usual matrix or multiplication? What do you think? Does it form a group under matrix multiplication? If I multiply 2 matrices, so let's start. To form a group, you check whether it's closed, right? So you check whether it's closed, whether there's associativity, whether there's an identity, whether there's an inverse. Okay. So since the determinant is 1, then you can be sure that there's an inverse. Okay. If the determinant were 0, then some of the matrices will have inverses, some will not. If the determinant is not fixed at 1. Okay. In this case, the determinant is 1, so it will have an inverse. Okay. Does it have an identity? Yes. So the identity will be 1, 1. Associativity and closure. Okay. Do you think it's closed? If I multiply 2 matrices, 2 by 2 matrices, if the determinant of A is 1 and the determinant of B is also 1, what's the determinant of C? Yeah. I'm trying to see the chat. Sorry, I'm come on. Sorry, I'm trying to see the chat and I don't know why it's not showing. Don't need to look at this. Because some of you have answered something in the chat. So why is my I don't know what's happening. If I want to stop sharing now, what do I do? Sorry. Please hold on a few minutes. Let me see what's happening. Okay, this is fine. Am I still online? Yeah. Meeting controls. Okay, fine. Okay, yeah. Thank you. Yeah. So we are going through the conditions. Determinant of C is actually, you can actually show that. We'll do it later. I'll give you this exercise later to do. You can prove that determinant of AB, okay, is if they are square matrices, is determinant of A, determinant of B. Okay. So you can show this. Okay. So if this determinant is 1 and this is 1, then determinant of C, which is AB, is also 1. What about associative? Of course, you take C, which is AB. If A is in the group and B is in the group, what about C? C will also be in the group because it will be a 2 by 2 matrix also, and the determinant will be 1. Okay, so it does form a group. So it does form a group. Okay, under usual matrix multiplication. Is the group abelian? What does it mean for a group to be abelian?
The element commutes.
Yeah, yeah. If the people in the group, if they commute, then we say it's abelian. Okay. Yeah. If they commute, then we say it's abelian. Sorry. How? Okay, so I do this. Why is it not? Okay, so I think I need to do this. Okay. This one, yeah, it's also called commutative. Okay, so in this case, is the group abelian. If I give you A and I give you B, I multiply them, is it the same thing as B times A?
No.
Is it?
No.
Yeah, so it's not. Okay. So in general, so the group is not abelian. Okay, so that's good. So in the next question, I give you a set together with 2 operations, addition and multiplication. Okay. And I ask if it's a field. So you need to read something about fields. So is this a field or not? Okay. So what are the properties we need for a field? There are 3 main properties we need for a field. What are they? Okay. So everybody, please do me a favor. Learn what a field is. And the next class, the first question is, not the first question. The next class, you actually have a quiz. Okay, Mubarak is telling me something. It should be closed under addition and multiplication operators. Close. No, closure is too weak. You need something stronger. So please read it up. I don't want to tell you. I want you to do a little work, read it up. Things like that. Okay, so let's move on to number 3, the third question. We consider two vectors, 1 and 2. Okay. The first question is, 1 and 2 are orthogonal. Are they linearly independent or not? Okay. So what do you think? 1 and 2? Okay. Yeah, Jean Bosco, you have an idea about what a field is. Yes, this is good. Okay. Yeah, okay. Yeah, you have an idea. And Jean Paul, okay, that's good. So please, okay. So in this case, you have two vectors, 1 and 2. The dot product of 1 and 2 is 0. Are they linearly independent or not? Okay. Dlamini thinks they are linearly independent. Who else thinks they are linearly independent if the dot product is 0? Okay. If you want to be purist, consider two non-zero vectors. So they are non-zero. So neither of them is the 0 vector. Okay. Are they linearly independent or not? Okay. So this is one place where you see the ideas you know from your ordinary vectors can be applicable to even things that we consider to be vectors in this larger context. I'll explain just now. Okay. So I will explain. I went to shut my door. I'll explain just now. So two vectors are linearly independent. Let me add a page here. Okay. So let's look at two vectors that are linearly independent. Sorry, two vectors, and the dot product is 0. In R3 space, I have one like this. Okay, and I have the other one like this. Okay. Let's call this 1 and this 2. Okay. So because this is R2 space actually. Okay. So you see, does the first one, okay, or let's call it A here. I'll call it B here. The first one, does it have a component along the second one? Does A have any component along the second one? So A, does it have a okay, if I draw another one, which I'll call C. Okay, so let's draw another, another one, which I'll call C. Okay. You can see that C has a component along B and a component along A. Okay. So I can say this vector C is something times a unit vector along B plus something times a unit vector along A, right? This C, okay? But you see, this
Yes.
to say it is 0 times the unit vector along B plus 1, sorry, not 1, plus something times the unit vector along A. Okay. So A has no component along B. So A and B are linearly independent. if A dot B is 0. Okay. So if they're perpendicular to one another, then they're linearly independent. Okay. So this I got from just observing in R2 space. Okay. But in general, it also carries to n-dimensional space. That if 1 and 2 is 0, that means 1 and 2 . Okay. So if they're perpendicular to one another, they're linearly independent. You can take a case like, let's say they are not linearly independent. Okay. That means 1 will have to be a constant times 2. Then you see that if you now do 1, 2, it will be 1. The constant is lambda. So sorry, let's do this. What I was doing will work, but I don't want to. Okay. So let's say 2 is a constant times 1. Okay. Then 1, 2 will be 1. And then instead of 2 here, I'll put lambda times 1. Okay. The lambda is lambda 1, 1. Okay. So you see, this 1, 1, according to our definition of dot product, this has to be greater than or equal to 0. Okay. Is 0 only if 1 is 0. Only if 1 is 0. Okay. But if 1 and 2 are non-zero vectors, then it is not 0. So in this case, you can prove it by contradiction. Okay. But you can also see what we have here. In the same way, also, if you say 1 is x, okay, and then 2 corresponds to the vector 3, x squared minus 1 over 2. And we say AB is integral of function a star b from minus 1 to 1. Okay. So you can see in this case, if you do the same thing for these two, you get this. You can do the integration, you get 0. Okay. So that shows you that x and 3x squared minus 1 over 2 are perpendicular to each other. Okay. When the dot product is defined by this integral. Okay. What about the converse? If they're linearly independent, is the dot product 0? Okay. So the fact is the converse is not true. Okay. A simple example is you look at this C vector. Okay. And B, they are linearly independent. I cannot write C in terms of B alone. I cannot. So C and B are linearly independent. So if I want to write C, I need something from B, but I also need something from A. So I can't write C using only something from B. So C and B are linearly independent. Okay. But you can see clearly that their dot product is not 0. Okay. So we go back. Yeah, so we answer this, we answer this. Okay. This we already did it just a moment ago. So this is an inner product, trace of A dagger. A dagger is what I define this way. The element of A dagger, ij, is AJI. Okay. Any questions? Okay. So the things you'll do today is like a motivation. Um, sorry. Here I show you a motivation quiz for what we'll do today. Okay. Can we write B in terms of C? Yes, we can write B in terms of C, but not in terms of C alone. We have to write it in terms of C and something else. So let me put it here. So you can write, can you write B? Yeah, you can write B in terms of C, something times C, but you will need something times A also. So you cannot write B just in terms of a constant times C. So, okay. So this cannot work in B and C. So B cannot just be, so B is not just that you scale C, you make it longer or you make it smaller. Okay. So this means you make it longer or you make it smaller, or you make it go back. Okay. So you make it longer if mu is greater than 1. You make it smaller if mu is greater than 1. Okay. In this case, mu is positive. Okay. Or you can reverse the sign. Means you make it go backwards. Okay. But you can see that B is not just some length times the other one. Okay. Is everybody still with me? Okay. So what we are going to do today is, can two vectors which are linearly independent be also orthogonal always? No, they don't have to be orthogonal. Yeah. Orthogonal. So actually later on we are going to talk about what we call the Gram-Schmidt orthogonalization procedure. You give me some vectors which are not orthogonal, but they are linearly independent. And then from that set, I'll form a different set which is linear, which is orthogonal. Okay. So it can be linearly independent but not orthogonal. Okay. A simple example also is this. So, okay. So let's look at these matrices. Okay. This one and this one. Okay. These vectors. We can see that they are orthogonal. So let's call this one A and let's call this one B. Okay. They are orthogonal. So if you find the dot product, ouch. Sorry, hold on. Okay. Yeah, so if you find the dot product, is 1 times 1, 1 plus 1 times minus 1. So A dot B is 0. Okay. Well, you can see clearly that you can write A as a constant times B. Okay. So you can, there's no constant you can have. So A is not the same thing as lambda B. Okay. And actually, if you want, you can draw both of them. Okay. A is exactly like this, and B is exactly like this. Okay. So this is A, this is B. Sorry, one is longer than the other, but they should be the same length. So you can write 1. This is 45 degrees. And this is also 45 degrees. So the total angle is 90 degrees. Okay. So they are orthogonal to one another, but oh, in this case, they are orthogonal, but they don't have to be orthogonal. I can give you an example where they're linearly independent, but they are not orthogonal to one another. Yeah, so you can look at C, which is 1, 0. Okay. So you cannot write A as a constant times C. Okay. But A dot C is not equal to 0. Okay. So you can think of different things like that. Okay. So what we will do today is we look at the vector, we look at vectors, and we'll be able to say whether two vectors are close to one another or not. Okay. This thing is more general than this. It's not just a matter of vectors. Okay. For instance, the color purple, do you think it's closer to red than to blue or to green? So nowadays, people are doing things called machine learning. And with machine learning, you have to be able to say like if, whether two images are the same or how close they are together or how different they are together. So even for colors, you can say whether two colors are close to one another or not. You have to define something called a metric. This is different from a metric tensor. It's just a metric that helps you to measure the closeness of two different things. And they don't have to be vectors in our traditional sense of vector. They can be any kind of objects, but once you decide the metric, and then that helps you to know whether they're closer to one another or not. So is color purple closer to red than to blue or green, than to blue or than to green? It turns out that you can use what is called RGB, red, green, and blue, to define colors. So you can mix colors together in certain proportions, and then you can have red, green, or blue. So each of the colors, red, green, and blue, they have a number. Let me see. Let me try to see if my web page is still open so that I will show you something. Yeah. Here. Okay. So this is the code for colors. So this RGB. Can you see what I'm showing?
Yes.
So this RGB, this shade of purple, you have 230, think of it like 230 parts of red, 230 parts of green, and 250 parts of blue. Okay. And then if you go, you can see there's Fuchsia, which is 255 parts of red, 0 part of green, 255 parts of blue. So you see this already formed like a vector for you. And then you can look at red would be 25500. That would be pure red. Okay. And then you can look at green also and all that. So basically, even colors, you can scientifically determine whether they're close together or separate from one another. When people do machine learning, they use these ideas of you have to define a metric, and once you define a metric, you can say whether this particular object is in this class or in that class. And so very applicable in different things. Okay. One of the things is we are training. So in research, there are things beyond what you read in textbooks that you need to be able to think of and apply what you are thinking to. Okay? So that's why I'm introducing you to this idea about even colors. You can say whether they are close together or not. Okay. Is a function x close to this function? Is function x closer to this function 3x squared minus 1 over 2 than to this function 1? Okay. Then we all know this expression. Okay. So what I mean by this expression is this: a dot b squared is less than, you can show that this is less than a squared b squared. This is easy to show in this case because a dot b is a magnitude, b magnitude, and cosine of the angle between them. Okay. This cosine can go from -1 to 1. Everything on the left will be equal to everything on the right. When it's +1, everything on the left will be equal to everything on the right. When it's in between -1 and 1, then everything on the left will be less than everything on the right. Okay. So this is true. Ouch. Sorry. My iPad behaves like that sometimes. Okay. Actually, I think I've pressed the wrong button. Okay. This is true for your two-dimensional vectors or three-dimensional vectors that we know from high school, okay, or from college. But even for functions, you find that you can show that, for instance, if you do this, okay, you square this is less than or equal to, you do this, and you do this. Okay. Okay. Then later on, when you do quantum mechanics, some of you already know. Have you seen this before in quantum mechanics?
Yes.
Okay. So what is this called? Yeah, you can just type it. So it's the Heisenberg's uncertainty principle. Okay. This you can show mathematically. Okay, uncertainty principle. Okay, good. So you can show this mathematically, and it comes from one of the things we are going to do just now. I think you'll have time to do it. Okay. Okay. So we are going to Cauchy-Schwarz inequality is what is used in quantum mechanics to prove this. And is the one that is a generalization of this A dot B thing. Okay. We'll deal with matrix and matrix spaces. That helps you to measure if two things are the same or not. And hopefully we'll try to start on orthogonalization of vectors. Okay, change of basis we'll probably do next time we meet. Okay. So when we were discussing the dot product, we introduced a new object, okay, the dot product that takes it takes something from V cross V and it puts it in the complex space, okay. So this V is V over the space C. Find this A and B as, so we define this dot product as some new object, okay. Actually, what we could have done is we could have actually defined a new object, which, so we have A, okay. We have A, which lives in V. We define a new object, A like this, okay, which lives in V star of K. Okay. This A like this is called the dual of A, okay, and this V star is the dual space of A. Sorry, is the dual space of V. Okay. So what this helps us to do is that then you can think of A dot B as just multiplying two vectors. Okay. That is exactly what you do. For every vector A, in V, we introduce another object. We call it the dual vector of the dual vector of A. So it lives in another space, which is called the dual space. What is the difference between metric and matrix? Oh, we'll see what a metric is just now. A matrix is a kind of a function. Okay. We'll see what a metric is just now. Okay. Okay. So an example is this. Let's say X is this X1, X2, one like that. Okay. Then we define or we introduce the dual, which we define as X1 star, X2 star, on like that. Okay. Then we can multiply X and X together. So in this case, we multiply the dual of X by X here is this X. Okay. So in this case, we don't have to talk about who is a dot product and who is not a dot product. Okay. So we introduce this. So we do a matrix multiplication. So if you follow the rule of matrix multiplication that we did before, so X1 star, X2 star, on, and X1, X2, and on. If you multiply both of them together, you multiply this together, what do you get? You use the same matrix rule like we had before. You get X1 star times X1 star times X1. You get X1 star times X1, and then X2 star times X2, one like that. Okay. You see, this is exactly what you call the dot product. Okay, I made a mistake. I mean, not a mistake, but I prefer if I had used Y instead of, yeah. Okay. So this is our XX. We call this the dot product, but it's just matrix multiplication. So you can do it for XY. It's just the matrix X1 star, X2 star, 1, and then this one Y1, Y2, 1, and then you get the same thing as we know you will get XI star, YI, sum over I. Okay. But in this case, I don't even say anything about dot product. I just say I take a multiply them together in this way. The dual times the so this brings out actually one thing before we go to metric spaces, and that's the fact that so I'll just make 2 remarks, and then okay, I'll make 2 remarks. The first remark is Yeah, the first remark is, you see, when we had this C and I had UA plus BV, okay, then you can see that this object depends linearly on U and B. I'm sorry, what am I doing? Sorry. This object depends linearly on A and B. Okay, so you can see that is something times A plus something times B. Okay, so it's something times A plus something times B. So it depends linearly on A and B. Okay. So let's define a vector W as AU plus BV. And then the dual of W, oh no, let's say W is A like this. Then the dual of W we define is as A star times U plus B star times V. And then you find that this dual depends, this dual times any vector, let's call it S, depends linearly on A star and B star. Okay. So this depends linearly on A star and B star. Okay. It does not depend. So this does not depend linearly on but when you do WS, okay? But if you do SW, if you, yeah, depends linearly on A and B. Okay. So if I had written C as S1 U plus S2 V, okay, then you see that C times, sorry, what am I doing? S1 U, dual of U plus S2, dual of V. You see that C times, let's call it a vector A, is S1 okay. So you can see that CA in this case depends linearly on S1 and on S2. So defining a dual vector helps us to, in a way, maintain this linear dependence. Okay, so not a dependent on the complex conjugate like this one, but it helps us to maintain a linear dependence. Okay, so now we have the tools to be able to prove the Cauchy-Schwarz inequality, and then after that we'll see if we can quickly get to metric spaces. We'll probably get to metric spaces, but not give an example. Okay. So a good reason to define the dual vectors is that You can just do matrix multiplication and not worry about thinking about dot products. Okay? So now we talk about Cauchy-Schwarz inequality. Okay. There are different proofs of Cauchy-Schwarz inequality. Okay. I'll give you a very simple proof of it. Okay. In this proof, you only need to remember something from high school, and that is it. Okay. So I'll give you a construction. Okay, I'll give you a construction. And so, but unfortunately, you have to remember the construction. Okay, so let's see. B A minus lambda. Okay. So this is a dot product, or if you like, you can say that this is multiplication of a dual vector B with a vector A. Okay. So let's see be defined by this. Okay. So someone will ask me, how did you come up with this thing? Okay. The thing is, this is not my proof. Many people have worked on this before, and they know that, okay, this will give you a simple proof. Okay. So this construction, later on, you'll see how this construction comes, because then I'll tell you something about projection operators. So then you have an idea how this construction comes. Okay. But in essence, so this lambda is a number, is a real number. It can be positive or negative or zero is a real number. Another way I can write this, I can say C is A minus lambda times B times something V. Okay. Or let's call it S. Okay. And then this S is your scalar product BA. Okay. Okay. So let's form CC. What do we know about CC? Is it positive? Is it negative? Is it zero?
Positive. No.
Okay. To be precise, it's non-negative. So we'll write it this way. Okay. And we don't have to know how you define your product. Okay, we write it this way. Okay. So let's do that. So since we already know what the dual is, the dual of this is just A minus, I have to do B here. Sorry.
Lambda star.
Lambda star, this B, I turn it the other way. If you like, you can say, so I can do B A star, but B A star is the same thing as AB. So here, I just have AB. Okay. So that gives me the dual. So I have AB, and then B, and lambda. Lambda should be starred, but I already told you lambda is real. Okay. So lambda and lambda star are the same. Okay. And then I put C here. Okay. So we can multiply out. You see, now I didn't say we do the dot product. I just say we multiply out because we've introduced what we call the dual. So it's AA, okay, minus lambda AB, BA minus AB DA lambda, and then plus lambda squared AB B D DA. Does everybody agree with this? So I just multiplied out. Okay. So let's look at this object. Okay. This is BB, is a positive real number, or at least non-negative real number. Okay. ABBA is the same thing as AB. Wait, well, let's say it's the same thing as Z times Z star, which is modulus of Z, where Z is AB. And then, of course, Z star is AB star, which is BA. Everything here is positive. Yeah, it's positive because this is modulus of Z squared. So everything here is positive. And I will denote this by P. Okay, everything here is P. What about this? This and this together, actually, you can write it as minus 2 lambda. Is ABBA. Okay. I'll call everything R. No, Q, sorry. So this Q is AD, BA. No, actually, yeah. It's the same thing as modulus Z squared. Okay. If you look here. So it's the same thing as modulus Z squared. Okay. And this AA, I'll just define it to be R. Okay. It's positive. So you have 0 is less than or equal to lambda squared P minus 2 lambda Q plus R. Okay. So this function, I will call it G of lambda. So you can see that it's a quadratic function, right? It's quadratic in lambda, okay? And it's always greater than or equal to 0, okay? So what does that mean? That means if you plot G of lambda, it's either going to be like this, or it's going to be exactly touching, okay? And it will never be like this. Okay. So this will never happen. Because if this happens, then you see it is not greater than or equal to 0. Okay. So I'm plotting as a function of lambda. So this is case A, this is case B, this is case C. Okay. Case A and B are fine because every time the quadratic is positive. Okay. Case C is not fine because for some values of lambda, it is greater than 0. So for some values of lambda, it's less than 0. Okay. So you can only have something like A or B. You have a quadratic equation. Okay, so if I give you something equal to 0, okay, you can find the roots. Yeah. So if I want, in this particular case, G lambda all roots in this particular case, G of lambda has one real root. Okay. What condition do we need to have these two, to have these two cases for this? What condition do we need? Okay. Okay, so I will kind of remind you. So if you're trying to solve G of lambda equals 0, then you get that lambda is, let's look at this thing. Is 2 lambda plus or minus square root 4 lambda squared minus 4 r 4 rp over 2. Okay, so for this equation, if you are trying to solve it, then yeah. So if you want real roots or imaginary roots, okay. Then you need the 4 lambda squared, sorry, not 4 lambda. It's 4q squared. 4 times q times, okay. So you need this minus 4rp to be less than or equal to 0. Okay. So that means you just need q squared to be less than or equal to rp. Okay. Let's remind ourselves, what is q again? Okay, q is just AB. So you need AB squared to be less than or equal to RP. R is A and P is this object. Sorry, I think I made a mistake. This is Q, right? AB, AB. Okay. So this is not Q. Okay, this is what you have. Then it's squared and it's less than or equal to RP. R and then B and P is AB, BB, BA. Okay. So you can see that this object here is real and positive. So I can divide by it and get AB, BA. I'll get rid of one of this and I'll get rid of this. So this is your characterized inequality. This one, we can write it as AB modulo squared because it's the same thing as AB, AB star. So you can write it that way. is less than or equal to this. If you like, you can write it as the norm squared of A. And this, if you like, you can write it as norm squared of B. If you are doing our vectors in high school, it will be A dot B squared is less than or equal to modulus A and modulus B squared. Okay. So this is your Cartesian inequality. And with integrals also, if you define an integral also, then you can write it as f star times g modulus of this squared is less than or equal to integral is of x. Okay, if you like, this is a star a of x. Sorry, I used the same limit ab. Sorry, fg. Dx. And here you have from ab g modulus squared dx. People have extended this to what is called the Holder's inequality. So you can show that this is less. Okay. So I will give it to you as an exercise to read what Holder's inequality is. Modulus of yeah. From this, Holder's inequality. What about it's easy to show examples for this quickly. I have a vector y, which is xi. The final step, I lost my connection. Oh, don't worry. If